Hello geometry class, this is Mr. Szabo, and we're going to go ahead and get started with our new adventure today, section 12.5 notes. I'm going to have a separate video that you've hopefully watched already, kind of introducing how we're going to go about this. If you haven't watched that, please go ahead and do that. So for the volume of pyramids and cones, what I want you to do first is take 30 seconds, take a minute, kind of make some predictions, start thinking about how you think those volumes compare, a pyramid and a cone, or how specifically a prism or a cylinder compares to a pyramid or a cone. I'm going to show a quick demonstration in about 5 seconds. So if you need to pause it to think this out, go ahead and pause. Alright, so what we have here is our cuboid or a prism, and I can change its length, I can change its width, I can change its height. Either way, it's still all going to be a prism. And you can kind of see in here we've got a green pyramid, a blue pyramid, and a red pyramid. And it's hard to see that until we start splitting these out. Now we can see that they are pyramids because they have one base, they have a vertex, and the volume of all three of those is exactly the same. That volume doesn't change if I change the length, the width, or the height of the cube or the prism. And what's nice is those fit perfectly in there. So this is trying to demonstrate is specifically that if we know the volume of a prism, then the volume of a pyramid that has the same height is going to be exactly 1/3 of that volume. So for a pyramid, it comes from a prism, and we know the volume of a prism is area of the base times height. For a cone, it comes from a cylinder, same thing. When we're talking about a pyramid, we now have to make it 1/3 the area of the base times the area of the height. Same thing with a cone. And the only thing we can say specifically with a cone is that we know the area of the base because the base is always a circle, so it's pi r squared h over 3. I am also going to provide a link to a video demonstrating this with water, taking water from a pyramid and pouring it into a prism that has the same height and showing evidence that it takes 3 exact pours from the pyramid to fill the prism up perfectly. Alright, so a couple of more quick vocab stuff and theorem stuff before we get into some practice problems. So we will be dealing with cross sections again. This time though, when we're talking about the cross section of a pyramid or a cone, it's not congruent to the base. With a pyramid or a cone, the cross section is congruent to the base. Now it's not. It is parallel. Cross sections and base are parallel, but they are similar figures now. So they share all the similar properties of our two-dimensional figures we studied earlier in the semester. And Theorem 121 says that in a pyramid or a cone, the ratio of the area of the cross-section to the base. So remember, area of a cross-section is this symbol here. Area of the base is capital B. That ratio is going to be equal to the square of the ratios of the distances from the vertex. So we're going to take another ratio and square it. Coming up with that other ratio is the one thing you have to be careful of. We're talking about altitude here. So if there's my vertex and I want to talk about this particular cross-section here compared to, say, the base section down here, we're talking altitudes are going to be what we're using for our similarity statements here. So vertex to here is one distance, that altitude, I'll call it K. The cross-sectional area, I'm taking the altitude to the cross-sectional area, so that's going to be in my numerator. And then vertex here all the way down to the base here. Let's see if I can draw that a little bit more clear. That I'll call H. That would be the altitude, just to not overlap in there, would be in my denominator down here. This is a useful theorem when we don't have as much information as we need, but it's not the theorem that we have to use all the time. And we're going to start to see that as we look at example 1 down here at the bottom. It's a theorem that I could use in this case because I can find the cross-sectional area, I can find the area of my base down here, but I don't have the altitude or the height of the entire cone. I don't think that's the most effective way that we can solve this problem though, so what we also can look at is the fact that I have similar triangles here. I have a right triangle where I know one leg and I don't know the other leg, and then I have my bigger right triangle here to here, and down to here, where I know this and I don't know this. And we can set up proportions to identify our legs, and in this case our altitude. So if I set up a proportion to solve that, using my right triangles, I know that in my smaller right triangle, I have x as my tall leg, and that corresponds to x plus 8 in the larger right triangle. And then the radius of my circle represents the other base, 18 over 24. We can then go ahead, cross multiply, solve this ratio. When doing that, we get x is 24. Now, if I draw these out separately just to kind of help us out, I know this has a height of 24 and a radius of 18 for this cone. And I have my other cone, which, if I try to draw that out separately, has an altitude of 24 plus 8 and a radius of 24. I am asked to find the volume of the frustum, which is this part here. So if I can take the volume of the large cone, subtract the volume of the small cone, I get the volume of my frustum. Go ahead, press pause, and try to finish that part off. So our volume for the smaller cone is 2,592 pi units cubed. The volume for the larger cone is 6,144 pi units cubed. When I subtract, I get a total volume for the frustum of 3,552 pi units cubed. And again, if pi is the only thing I would be rounding, I don't want to round it. I want that as an exact answer with pi in my units. We're going to see an example in a minute where we don't have a choice but to round, and in that case, rounding by multiplying by pi is also acceptable. Alright, so to wrap things up for this video, I want to try to find the volume for 2 and 3 in the back, please. So for number 2, the volume part was relatively straightforward. The area of the base part was the one that can get a little tricky. We have to recognize that it is a hexagon, and therefore the apothem is going to be formed by taking half of one side length, and then we have a 30, 60, 90 triangle. And for number 3, we need to use our tangent formula, start to use our right triangle trig. So those are also skills that we can't neglect and can't forget. So the tangent of 42 degrees is equal to 6 over r, so r is 6 divided by the tangent of 42. At this point, if you're going to round that, round it out to as many decimals as possible, because we are using that for something to start calculating our volume. So in this case, the volume is going to be equal to pi r squared, but this is our radius. I sometimes like to just type that in, 6 over the tangent of 42 degrees, and then times our height times 6. If you did that and you rounded it, great. Just round out to as many decimal places as you can. Now this is the example I was talking about prior in this video. I have to round this. I don't have a choice. There is no exact answer unless I leave it in terms, that should have been squared, unless I leave it in terms of tangent, which we're not going to do. It's not something that's the proper way to do this, so I will round that. When I solve this, I get then approximately 88.809 pi units cubed. But since I've already rounded my coefficient, that's the time where it makes sense to just multiply by pi and round again and get that the volume is approximately 279, well, I'll just say 0.002 units cubed. If you just said 279, that's probably accurate as well. Again, since we're rounding, we're going to be off by decimals here and there depending on where and when we rounded, but I would highly recommend waiting and not rounding until as close to the very end as you can. Alright folks, go ahead and you can get started on your homework for section 12.5, and I will be releasing a video in the next day or so regarding homework policies over our e-learning and what we're going to be doing and expecting with that.